So the first approach, we looked at it, the numeric approach to calculate the bending moment or shear force at any point in a beam. It's doable, not very hard. The problem with it is just lengthy procedure, especially when you have a long beam and too many forces applied on that beam. That will create lots of steps that has to be done. The sign convention is an important thing for us. This sign convention, keep that in mind. And keep in mind, most of the work we'll be doing from this point onward will be on this side of the beam, in theory, because we will try, as you see, as we go through it, we will try to start analyzing the beam from left to right. So we're always looking at this portion here on our right hand side. So we're starting from this way. We're always looking at this portion of the beam. Okay. The second method for this, for drawing bending moment diagram, shear force diagram, the application of the method is very easy, graphical application. Just by adding some rules there, we have mainly 3 rules. We'll talk about them at the ends, these 3 rules. But until we get there to understand them, we'll go through them step by step. We will use these rules for our drawings or for the graph that we are trying to produce. But obviously, this is based on mathematical understanding from integration. Okay, we are simply trying to integrate the loading diagram. If you integrate the loading diagram, that will give you the shape of the shear force diagram. If you integrate that shear force diagram, the graph of the shear force diagram, that will give you the bending moment diagram. I'll explain this a bit further at the end. Will make a bit more sense. Okay. This is just for your understanding. The shear force diagram and bending moment diagram, we'll start with the first one, which is the shear force diagram. Both will have similar rules. Sorry for that. So both will have same rules in theory. We start with one of them and then we'll move to the other. So let's start with the shear force diagram. If we need to draw the shear force diagram, having said that, sorry, both are similar, but we have to draw the shear force diagram first, based on this understanding that the bending moment diagram, it's the result of integrating the shear force diagram. So to be able to draw the bending moment diagram, first we have to start with drawing the shear force diagram. So the sequence always, free body diagram. So this is the beam. We have to go through one step to draw the free body diagram first, then shear force diagram, bending moment diagram. Now, to draw the free body diagram, obviously it's essential that we do our reactions correctly. Therefore, I will emphasize again, please go back and check your study about calculating reaction forces. If you guys are having problems with that, please let me know. I'm more than happy to spend time and review that with you. I'm sure Mike did everything about it and you guys good at it, but maybe if you didn't have the chance to review it and study it properly, please do that. If you have any questions, more than happy to answer them. Okay, so the shear force diagram. The first thing we need to agree on, as we said it many times now, we are looking at drawing this shear force diagram. So if I need to draw this shear force diagram, my starting point from the left. I'm going to start from left to right. By adding these rules, we will come up with steps to come up with this diagram here. Just so you understand, this diagram here is just showing the value of shear force at any point. You remember when we calculate the shear force here from this beam at point B, which is 5 kilonewton. So that means if I need to ask about the shear force value at a point here, let's say A, B, C, D, E. Let's say there's a point E here. I need to find the shear force value there. I could either take a section at this point, or by just looking at the shear force diagram, this is point E. Looking down, this is point E. The shear force value there is negative 20 kilonewtons. Negative, that means it's facing down. Okay, because we agreed. Look from here. I'm looking at this portion of the beam, the right-hand corner, up is positive, negative is down. Okay, we'll explain that a bit further. Let's not worry about these details now. The rules, the first thing tells us, so we're starting from left to right. The second thing tells us, if you have a concentrated force, the shear force diagram will be affected. And the effect of the shear of a concentrated force, that will be a jump or dip, respectively, if you have it upward or downward. So the concentrated force could be upward, like the reaction, could be downward, like this 40 kilonewton. So the first rule tells us, if I have a downward bending, downward concentrated force, that means the shear force diagram will dip, that means will go down by the amount of force and the same direction. And if I have an upward force like the reaction here, the shear force diagram will jump, go up by the amount of reaction. For me now, looking at this shear force diagram, I moved from negative 20 to positive 26. That means I know the reaction force here is 46. Because that moved my shear force diagram 46 up, from negative 20 to 26. Positive. We'll explain that a bit further. But the rule says, if we have a concentrated force acts upward or downward on the beam, the shear force diagram will jump or dip, respectively, downward or upward, in the same direction of the force, by the same amount of the force magnitude. So it depends on the magnitude and the force, that will move my shear force diagram up or down. Very simple. The second note we have there, parts of the beam where there's no forces acting, this will result the shear force diagram being constant and maintaining its last value on the left hand side, so the one before what we got to. The direction where we started, yes, that's where we started from. In other words, if I look here between, I have an upward force here, the reaction, I have a downward force here, the 20 kilonewton. The 20 kilonewton based on the first rule should move the shear force diagram downward, because that's a downward force, by 20 kilonewton down. That's what I did. In between these two, I have no forces. Can you see any forces here? I've got reaction, point load, nothing in between them. Therefore, the rule tells you, in between these forces, the shear force diagram will maintain its last value. The last value here was 20. The shear force will try to maintain that along the entire distance until something else will change it. Another force will change it. If you find one of those not understood, please stop me so we can explain. Are we agree? Are we clear on 1 and 2? Okay. Now, the third rule says...
Sorry, Aaron.
Yes, mate?
So just a recap of the point 2. So
yes.
That means that starting from A going to B, in any cut we do, we'll have 20.
Sorry, can you say it again? In any what, sorry?
So starting from A to B,
yes,
everywhere we cut, it's
yes.
going to be the same value.
Exactly.
Okay.
Because nothing is changing that. All what's happening here, do you remember the particles we're talking about?
Yeah.
We talked about earlier. The particles here suffered from 20 kilonewton acting downward, and there's nothing yet balanced there. They're still just acting here, transferring that 20 that way. Okay?
Okay. Thanks.
No worries. Okay. Now, in the case of if we have a downward uniformly distributed load, we're all clear on the term UDL, uniformly distributed load. Anyone, guys, doesn't know, please go ahead and ask me now. As I said, all of those are important for us today. We're all clear on uniform distributed load. Okay. If we have a uniformly distributed load acting on the beam downward, the shear force diagram will be a declined line. So it won't be straight line, what we had here before, or just jump or dip. Will be a declined line for the entire length, obviously, of the uniform distributed load. The change in the shear value, V, between the start and the end of that declined line is equal to the area under the distributed loading curve. So this is a bit too much info. We'll put it to sleep for now, and we'll look at it in details down the track. If I have a uniformly varying load, do we all know what UVL is? Uniformly varying loads, UVL, the triangle. I'll show you some examples of those today. Acts on the beam, the shear force diagram. The shear force diagram will be a decline parabola this time, rather than, it won't be a line, will be a parabola, which is curve, a second degree curve. The parabola is the graph of a second degree or a quadratic equation. We'll talk about those later. And a change of the shear value between the start and the end, the same thing, of the declined parabola is equal to the area under the distributed uniformly varying load. We'll talk about these two in more details. We'll explain. Now, an important point that will give you a sense of check for your work: shear force diagram should start from 0 and should always go back to 0 at the end. Okay? We should get, by the end of the shear force diagram, we should be starting from 0 and then we're going back to 0. Okay. Let's put this into practice. I know it could be, so let's take the first case, which is concentrated forces. Let's put these two to the side for now. If we have a concentrated force, point load or concentrated force, we agreed we have two cases. If the point load acting upward, that will cause a jump in the shear force diagram, and the amount of that jump, the value of the shear force diagram jump, equals to the same amount of the force magnitude. So if I have 20 kilonewton, that will make the shear force diagram jump by 20 kilonewton if I have it upward. If I have the 20 kilonewton downward, that will cause the shear force diagram to dip or go down by the same thing, same direction and the same value or magnitude of the force. Very simple. Now just keep in mind what we agreed on. Parts in between the point loads will maintain its last value on the left-hand side, which is the direction we're coming from, or we're starting. And the shear force diagram will start and finish at 0. Okay, rather than worrying about just too much theory, let's put this into practice. The first step is to first of all draw the free body diagram. We agreed on this. We can't do anything without doing the free body diagram. So what would be the reactions here, guys? Let's say this is point A and point B. What would be the reaction at point A and point B, please?
10 kilonewton each.
Thank you. Somebody that's just looking at it quickly. 20 kilonewton down at the same distance from both reactions, or both supports. That will create similarity reactions between them, 10 each, okay? Equally divided between the two supports. So the shear force, the free body diagram will look like that. Very simple, okay? Okay, so that's our starting point. So that's our beam, free body diagram. That will allow us to start drawing our shear force diagram. And let's analyze what we've got there based on the rules we learned. I've got a force acting upward, another force acting downward, another area between the two forces has no forces acting on it. Anything not clear about this, guys? Okay. We're all clear about this terminology here? Straightforward, right? As I'm telling you, like this shear force diagram, bending moment diagram methods are very simple, very easy. They make lots of sense. They are high school level, kind of. But they give you very good tool for designing, and they get some complicated, we'll talk about them, but they are a very good tool to design your beam. So based on what we learned, if I need to start drawing the shear force diagram, the first thing we agreed on, I have to start from left. I'm starting from here. These rules, guys, will not work if you start from right. And now you understand why. Because if I start from right, everything we are assuming should be the opposite direction. That will throw lots of your calcs in the opposite direction. So let's all agree on it's required that by all references almost, when we start drawing shear force diagram, left to right. Okay, so based on our understanding, what do you reckon the first thing I should draw in the shear force diagram, guys? Anyone will be able to turn on your microphone and let me know, based on what we agreed on, and based on the free body diagram that you can see. What is the first thing I may see on my shear force diagram here?
Positive way and 10 kilonewtons.
Can you say it again, please? Positive, Ina, sorry.
Positive.
Yes.
Positive section. So.
Yep.
Up way.
Yep. So it's we agreed on we should see a jump or going up on the shear force diagram because the force is acting upward in the positive direction.
Yep.
And by 10 kilonewtons. So if we look at that, that's what we should see, simply. I started at 0. This is my 0 kilonewton. That's my reference. The beam is my 0. I started from 0 based on our first agreement that if I have a force acting upward, that should result in a jump of the shear force diagram by the same amount and the same direction. So my shear force diagram should move up, starting. Good. Now, the next thing. What do we see here? An area of the beam doesn't have any forces. Look at it from this point here, from A to B. There's no forces acting. That's it. At the location of the force, we added that. Then I have to continue from that point. I'm here already. But here there's no forces at all acting. So what will happen? The shear force diagram will maintain its last value, which is what we have on the left-hand side. So we started by 10, no forces. That means that will continue as is, no changes there. And then what will happen after, do you reckon, guys? Anyone will tell me what will happen afterwards?
It drops 20.
So what would be the value? Fabio?
Minus 10.
Perfect. So because I have another force now, that will continue all the way, all good, no worries, until we'll hit this force. This force will force the shear force diagram to go down by the magnitude of that force. So that will force it to go 20 down. That will cause a dip of 20 kilonewton. From 10, take 20, that will be negative 10. Okay? And after that, anyone will tell me what will happen after? I'm already at negative 10.
You straight to the left, to the right, sorry.
Perfect.
And
So
go up again.
So because I've got this part here, doesn't have any force acting, that means the shear force diagram will maintain its last value. And then I will hit 10 kilonewton positive, that will move it up. And look at it, shear force diagram started at 0 and then ended up at 0. Okay, so if the shear force diagram doesn't finish at 0, you should know there's a problem there. All good, guys? Any question about point loads? It's straightforward. Really. Okay.
So good.
Yeah. Go ahead. Yes, thank you, Seth. Thanks for asking that. I need you guys to ask if you have any doubts. I'm listening. Oh, sorry, you're saying it's all good. Fair enough, all good. Okay, so this is our, in theory, that's our product. With using that very basic rules, we draw a shear force diagram for the entire beam. And look how easy is that. I don't need to take a cut at any point here. I can take, if I ask you at any point of this beam, you can easily tell me, Aaron, at any point between A and B, the shear value there is positive 10 kilonewton. At any point from B to C, let's say, will be negative 10 kilonewton. Okay? So positive or negative doesn't matter. It's all about just, it's a direction. Both are affecting the beam equally, but it's just a direction, okay? Is it from right to left or left to right? That's all what it is. So these are the rules again, and that's the shear force diagram. If we have a point load acting upward, this will cause the shear force diagram to jump up by that amount of force. If I have a shear force acting downward, that will cause the shear force diagram to dip down by the amount of that shear force. And if I have an area between two shear forces, there's no force applied there, an area there's no uniform distributed load, there's no point load, there's nothing, there's no shear forces mainly. It doesn't matter. I may have moment, I may have normal forces or axial forces. Those, they don't affect shear force diagram. All what we're drawing here, all what we care about, just shear forces. If I have that portion with no shear forces on it, that will maintain its last value. Wherever the last value was, will go straight. All right then, if you're that good, let's look at this one. Can you please try to calculate or draw the shear force diagram for me on this? Start with, I need to draw the free body diagram. And to draw the free body diagram, I need to know the reaction at A and reaction at B. Before I start, Fabio, do you have a question?
I was going to ask, but I think I know the answer. Like in the previous example.
It doesn't hurt to ask. Go ahead, try.
Okay. Just can you come back one? Yeah, that's okay. All right. Okay. The shear force diagram. So we've got the left side 10 kilonewtons. I suppose that if I had a force going down at the half of the first half, going down 2 kilonewtons.
Here?
So it will drop from 10 kilonewtons to 8 kilonewtons and then go straight away into 10 kilonewtons again?
No, so you're saying if I have a 2 kilonewton here?
Yes.
If I had a 2 kilonewton here, that 10 will go until we reach that 2 kilonewton.
Yes.
That will drop to 8 and then go straight away to 8.
All right, yeah.
And then whatever the value here would drop. But keep in mind, just don't forget, Fabio, if you have a 2 kilonewton here, your reaction forces anyway will be different. It won't be 10 and 10.
Yes, but just to make sure.
Yeah.
Okay.
That's what we'll be looking at here.
All right.
So, can you please, to start with, all calculate for me the reaction forces at A and B? And I need the answers from everyone, please, this time. Okay, when you finish, please keep your answer for yourself until I'll ask you all to provide the answers. Can we pause recording so we don't make it very long for you? No, we can't. when you're done, please, can you type just done? So I know how many people are still working and how not. And we can just start looking at that. Thanks, Ina.
Hey, Aaron. What in toilet? What are you asking us to do now?
Sorry. I need the reaction forces at A and B.
Okay, just this, not the diagram.
I'm asking at this point to get there first. Let's all get the reaction forces because that's our step one, right?
Okay, okay. Just a second.
So when you're done, please just write something down that you've done. So make sure everyone with us on the same page. Guys, for the people that may feel a bit behind, I don't want no pressure at all. Me, myself, when I was doing this, I was very slow. It's all part of the progress, working, practice, okay? So I'm not making pressure on anyone, but I just want you all to participate. Using your calculator, using the numbers, refreshing your knowledge on calculation is a skill by itself. And I think I should stop talking now so you can focus. Thanks, Jan. That's good. I didn't hear anything from you at all today. Perfect. Good. Okay. Since Ina, can you type the values for us, Ina, please, for the reaction forces? Okay, so I've got 33.57, and at point B, we've got 16.43. All agree, guys? Anyone disagree with these numbers?
Good.
Okay, thanks, Saverio. Okay, perfect. Well done, for everyone got the same. If you didn't get the same, it's even better, trust me, because making mistakes is the first step to learn something. Okay, and trust me, you'll never stop making mistakes. It's all about just the mindset, clarity, practice, and all of this. You see, even me, sometimes I'll make mistakes. I don't practice those for a very long time now after using all the Excel sheets and this and that. But the point is, we try all the time. Okay, so we've got the reaction forces and we can draw a free body diagram. So I can just add here these reaction forces. With what do we have there? Yep. We've got 33 here and 33.57, 16.43 there. Okay. So I'll just 33.57. Where's Bruno? I didn't see anything from Bruno. Is he with
Yeah,
us?
16.42. Oh, 43.
Okay. Good.
No.
That's for what?
Oh, for maybe I got a different result.
Logically speaking, this should be higher reaction. 4, 3. Bruno, logically speaking, look at these. I've got higher forces close to this end, so I should have higher reaction here, smaller reaction there. Most of the forces are closer to A more than B. These are the things you can judge your work. Everyone agrees?
Yeah, exactly.
Okay. So these are our forces, guys. Now, based on this understanding, what is the first thing we should see on our shear force diagram? Can you start drawing your shear force diagram? All what you have to do, this is your free body diagram, correct? So all what you have to do, draw a line, the same length roughly as your beam. Usually what we do, we draw it exactly underneath it. Let me just take this to the whiteboard. Let's go with that. What we usually do, guys, it's way easier on paper rather than here. We draw a beam underneath that, the same size as our initial beam. And if you'd like to make it a bit more organized for yourself, just as a starting point until you get the hang of it, you can start just drawing these lines here, just so you know where is what. Dashed lines like that. These are the milestones, the important critical points for us. Okay, so this is our beam. We can call it A, B. Okay, based on this, is that 100%? Okay. Based on this, what should happen here at the start, based on our sheet or free body diagram? Anyone can tell me?
Up 33.57.
Perfect. So here, just to give you some hints about this, try to come up with a scale, a very basic scale. Doesn't have to be something very sophisticated. It's just a basic scale. So in other words, don't make here, if I'm saying this is this, if I'll assume this square, I'll assume this square is about 25, for example, okay? If this square is 25, that means 33 will be somewhere halfway through the second square, up to here. That's 33 point, roughly. That's what I'm saying, it's rough scale. So that would be 33.57. Just make this easier for me here. Okay, all good. So that's my starting point. That means I have to go up by that distance there. If you can use rulers, it would be much better. I can't here. And after that, what will happen?
Draw a line like straight away to the point C.
Okay, so that means we agree between A and B. There's no forces acting there. That means I'll maintain the same value for shear force diagram. We'll go straight horizontally. At point C, let's look at that. What will happen? Anyone else other than Bruno?
Drop 25.
Going down.
Perfect. Yeah, that's good. Everyone with us on the same page. So we'll go down by 25. That's why, guys, I chose a scale. So we can know how much roughly we should go down. I need to know, is it 25 here or there or down below that? So 25 is roughly about one square height. So we'll be roughly about halfway through to that square. That's 25. So I was at 33.57 minus 25. How much would that be?
8.57.
13.57, right? Sorry.
No, 8.
8.57, yep. My value here. Okay. Then after that, obviously, we'll go straight because there's no action here. And then we'll go down by 5. I was at 8 minus 5, that will be 3.57. Positive all of those. And then I'll go at that value. And then go by 20 down. So I was 3, I need to go 17. So I should stay within the first square, not too much. And so 20 take 3.57 will be 16.43.
Yeah, yes.
16.43. And then I'll start going straight. Look at it. 16.43. That means I'm going to 0. All good? See, now rather than taking section here, section there, another one there, and try to calculate all these forces, straight away, if you ask me at this point here, I'll tell you the shear force value there is 33.57. That's what it is there at any location. In between those is 8.57 positive. In between those is 3.57. In between here, 16.43. All right, guys. Anything difficult about what we've done? And please, I would like to hear from people. They may have something not very clear or problems. Are we all good, guys, with that?
Could you please just back the slide before?
That one there?
No, the exercise, the one that you just did, not before. The whiteboard, I don't know, what did you call it?
Yeah, okay, yep. Yeah.
Thank you. Yes, thank you. Thank you so much.
No worries. That's, I was showing you this, it's a bit clearer, the same thing here. That's why I showed you.
Okay, much better, yeah.
Please let me know when you're done.
Done.
Okay, good. Okay, obviously, guys, you all know I don't want you to worry about copying this because you will have those after the lecture, right? Okay, so this is all what we have to do for point loads, guys, and that will cover big portion of the shear force diagrams, but we still have different type of shear forces. We have the uniformly distributed loads, that will be as a shear force, UDLs, because they are forces applied on the beam, acting at 90 degrees. You've got uniformly varying load, that triangle shape, that's still applied at 90 degrees. All of those considered as shear forces. So we still have a few other cases we need to discuss. But for the point load, which will play a big part, and it will be always in any case, because we always have at least 3 actions. Do we understand what we are doing there for the point load? Right there. In a uniformly distributed load, let's take the case for a uniformly distributed load. Based on what we discussed, guys, it's very similar, but the effect of uniformly distributed load is slightly different than point load. If we have a uniformly distributed force acting downward, the result in shear force diagram won't be just a dip, sudden dip or jump, will be gradual decrease or gradual increase. Why is that? Because each one of these loads from the uniform distributed load will make small change, small dip. Okay, we have infinite number of those next to each other that rather than making a sudden jump up or dip, that will make gradual decrease or gradual increase. So the UDL forces, if it was downward, that would produce declined line. That means going down. Negative will produce downward is negative. Agree, guys? So this 10 kilonewton is negative as a shear force, if you remember from our sign convention. We agreed we're always taking a imaginary cut at these points and looking at this side of the beam. That means the shear force should be up positive. So regardless, you can, if you'd like, memorize it. If you'd like, you can simply just memorize it. In shear force diagrams and bending moment diagrams, the forces acting down are negative. So if the force is downward, that means if it's negative, that will produce declined line. And if the force is positive, that will produce inclined, going up line. Therefore, how much does it go down? Sorry, how much this line will go down or go up? If you remember here, the amount of dip or jump was the value of the force. Similarly, the incline down or the decline down or incline up is the amount of the overall force, the area here, which is 10 kilonewton, that's the magnitude, multiplied by 4, the distance. Make sense? What do you guys think? All good?
Yeah.
Okay. So that's the only difference between the two. So UDL downward will make a declined line, UDL upward, inclined line. The amount of inclination or declination will be equivalent to the magnitude of the overall force. And the same rules will apply if, in case we have a small portion of the beam that doesn't have UDL, doesn't have point load, because you may have, in here, we have the beam all together has a uniform distributed load, but we may have a uniform distributed load here, then a gap, then another uniform distributed load there. You may have all kinds of scenarios, like this one, for example. I have uniform distributed load here, then a gap, then point load. If we have that area where we have uniform distributed loads, where we don't have any forces, that should maintain the same rule, will maintain its last value. And again, shear force diagram should start at 0 and finish at 0. Any questions about that before we look at this example? Okay. Can you please draw the free body diagram for this beam? AB. When I'm saying draw the free body diagram, your main task to calculate reactions. So we have a UDL here. Assume this is a UDL, 10 kilonewton per meter. That means I'll have reaction here, reaction there, of how much? And I will ask for this one. Someone, Tiago,
Yep.
what are the reactions at A and B?
20.
Should be 20 kilonewton each one.
Yep.
Thank you. Okay, so this is the free body diagram done. Shear force diagram. What shall I do as starting point? We're starting from left to right, always. And my starting point always 0. What happens there? Anyone will tell me.
Going up
How much?
20.
Perfect. So what Ina's saying, because I've got the point load here, that's the first thing we have is the reaction. I've got the point load 20 kilonewton upward. That means I have to go up by 20 kilonewtons that way. And that will be 20. Positive. What happens afterward, based on what we learned? For the UDL, what we'll do for our shear force diagram, if we have a uniform distributed load, that will produce, first of all, is this force positive or negative? The 10 kilonewton, is it positive or negative, guys?
Negative.
Negative.
Negative, perfect, because that's always facing down, negative. So, what will happen for the shear force diagram? That means, what is the product of it?
It's you going down, straight line going down,
Okay,
and at the end, 20 top.
okay, so,
With a slope.
yes. So that will be declined line, will be diagonal, declined line, something like that. And that will be challenging. Actually, it's better to use a ruler to draw it straight. There we go. So that means I have to go from here, declined line. How much will it go down? I know, all I know, this is the shape. That's all I know so far. But how much down? Why this much? Not, for example,
Aaron?
that much. You know, or that much. How would I know?
It's
So,
because you have a reaction force on the other side.
Yes, so
so the idea behind is because you know that at the end should be 0,
mhm,
and then the second reaction, 20,
mhm,
should be going up to 0. That's the should be this, must be this.
Okay.
So that's why the UDL that starts on the plus 20 and go to the minus 20 at the end to then come up to 0.
Okay, guys, you are making a mistake here. Then it's correct. That will be the right answer.
Can I have a go?
Sorry.
Can I have a go?
Of course. Yes, please. Go ahead.
I think because the UDL it's 10 kilonewtons per meters and we have 4 meters, the total gonna be 40 kilonewtons centralized. So 2 meters of the point A and 2 meters of the point B.
Perfect.
So in the center of the beam, we need to go down 40 kilonewtons.
In the where? Sorry.
In the center of the beam, in
Yeah.
2 meters after point A,
2 meters after point A. Yes.
we need to go 40 kilonewtons. down. For this reason, after this,
Yeah.
we're gonna have the 20 kilonewtons up in point B. So it's going to reach the zero again on point B.
So you made a very good start, Stella, but I'm not sure about the end there. What are you saying? Let me understand properly what you're saying. What you're saying that we need to go straight and then down 40 Newton and then straight and then up 20 Newton. 20. Is that correct?
No.
Just
No, you have to go inclinated with angle.
okay, that's good. Okay, so guys, I'll just go back one step to the guys. All what they said, the first guys, they said, "Oh, why? How would we know how much we go down?" Most of you answered, "We should go down to 20 because I know there's a 20 kilonewton here." Correct? That's the first group of people opinion. And that's correct in this case, but this will make you make lots of mistakes and incorrect in more complicated cases. You'll see down the track, you see a good mix of different forces, very hard to judge from the end of it. What you should be saying, yes, anyone would like to say something? Can I just continue, finish this one, please? What you should be all saying, guys, we started at 20 kilonewton. All what we know that from the shape perspective, we know that this is an declined line. And how would we know how much? It's the value of the force here. I don't care what the reaction. I started at 20. I should be by the end of the UDL going down 40. That's all I know. I don't care what is the reaction here. Because in this case here, you have a full reaction to go back to zero. What about if I have a long beam and I have another force here? It doesn't take you to zero. It takes you to some point, then there is another force as you go. So this shouldn't be your indicator, guys. Okay? What should be your indicator is this, what you are going by. You are going by a uniformly distributed load of 10 kilonewton per meter, and you have 4 meters of it. That means every 1 meter I'm going 10 kilonewton. 2 meters, 20. 3, 30. 4, 40. Or it doesn't just, you don't need all of this. All what you need to know, just do that. All what you need to know, I'm starting from 20 and I should be ending by 20 minus 40. The value here, 10 by 4 is 40. 20 minus 40, that will be minus 20. So I don't care what the reaction at the other end. The reaction at the other end should be used to check my results, not to give me the results. So I should be saying I'm at 20, I'm going down by 40. That means I'll start here and I go down to a point by 40. If I do that, I've started from 20, that means I'm at negative 20. And then I can check, okay, I've got a reaction of 20, that means my work is correct. I'm going back to zero. Do not make your shear force meet you where you think it should meet you. You shouldn't do that. I'll give you lots of examples down the track, you'll see them. This force to check for you, not to tell you. This force here, that by the distance, should tell you how much you're going down. We're always working from left to right. Don't use anything on the right as information. Clear? Did it make sense what I'm saying, guys?
Can I just add something?
Yeah,
mate. This straight line that you draw should be actually a curve that goes like a cosine function. So that starts at plus 20, gets 0 in the middle, and goes to minus 20.
Not as a curve, you mean, right?
Yeah, I mean, as in reality, should it be like a curve?
No. I think it's confused with the moment diagrams.
Yeah, we'll talk about moment diagrams down the track, Severio.
Okay.
We'll
Okay.
talk about that down the track. So look, focus with me on the shear force diagram. You'll see bending moment diagram is just like this after you understand this, because it's exactly the same procedure. Okay? Let's try to understand one thing at a time, please. Okay? So we all agree with this, guys. Did we understand how do we establish this? The thing here I need to make sure. First of all, I need you all to know that's what will save us, we'll use for bending moment diagram. This portion here is positive. This portion obviously is negative, all this area. Think about it this way, guys. In terms of mathematics, if you would like to talk about mathematics, your uniform disputed load here is uniform, like it's just straight line here. Look at it, I can't draw a straight line, but it's a straight line here. Always constant value, 10 kilonewton per meter, constant. Someone asked me about the bending moment diagram. We'll talk about that in a minute, please, Paolo, if you don't mind. So, the point I'm trying to make here, your UDL here, the shape of your UDL is a straight line. The equation usually for a straight line is y equals to a constant. In our case, equals to 10. Your force always equal to 10. Okay? Straight. Based on the integration understanding, if I integrate a equation for a straight line, what would that give me? What's the one level up? Should give me a diagonal line, right?
Yeah,
a line with a
diagonal line.
slide. Yep, inclined line. Inclined or declined, that's why we're calling it diagonal. So that will be a line with a slide on it. Okay? In this case here, it just will be 10x, the integration of that. And that's what gave us here. Look at it. It depends now, because this is, we were wrong here. This is not y equals 10. This is negative 10. Because we agreed, this 10 kilonewton is a negative value. That's why the second equation equals to y2, let's call it if you'd like, for the second line, negative 10x. Okay, so it's a negative negative declined line, negative slope on the line. All good? So the point is, the whole point, just I want you to get it into your head as very basic terms. I don't want to go into maths. We don't want to spend time on that. If our force is a uniform distributed load, that means it's a straight line. That should, in theory, in your mind, straight away, when I see UDL, I should get declined line or inclined. One of the two. Depends on, is it downward, that will give me decline. Is it upward, will give me inclined. Okay? This is rule number one.
Aaron?
Yes, Mike.
Okay, I understand the way I have to do, but why after the second half is negative if the force is
negative?
Yes, like why we have this
I'll tell you why, if you don't mind.
All right.
Happy.
Because the force is distributed, is 10 kilonewtons per meter everywhere. So why do we have this changing point?
Yep. So let's say, talking about money, Bruno brought it up this morning. Bruno's situation, let's discuss Bruno's situation, because he was asking about money this morning. Bruno, at the start of the year, he had $20,000 in his account. 20,000 or $20, Bruno? What do you reckon? So Bruno had $20,000 in his account at the start of the year. Every month, that's after 4 months, every month, Bruno is spending 10,000. The first month, his bank account turned to 10,000 only because he lost already 10,000. The second month, he doesn't have any money. The third month, he is negative. He's using credit now. He withdrawn money from the bank by negative 10,000. The last month, he's negative 20,000. And that's where he asked me for money. For the 20,000 here, he went back to zero. All good? Paolo?
Yeah. Yeah.
Fabio was asking. Yep, makes sense, Fabio. Okay, so what we're saying here, we started at a positive value. We are losing on constant rate, which is 10 kilonewton per meter. Then we got to a zero. Then we're still losing we still having forces in the negative direction. But then we went back by adding the reaction, we went back to zero. All good, Bruno? At least you bite your debts. All right, guys, makes sense? Seriously. Now, this could be for, just think about it, anything. So you've got a reserve, you are spending from that reserve, and then you're adding one value at the end. All good? Okay. If that's okay, then can you all look at this case for me, please? And I want you guys, please, to correctly calculate the reaction forces. Please take into account you have a moment there. Don't ignore that. Take the reaction, calculate the reaction forces first. If you are done calculating the reaction forces, please say I'm done on the chat so we can make a start on it, okay? Unless you have a question. Yes, please, go ahead.
Should we decide the point name?
So
We just have A and B, so
okay. So let's, if you'd like, we can. Okay, I'll type something for you here. A, B. Let's call this one here C, and D. If you'd like. Okay. Thanks for that, Ina.
maybe we need a middle point. Maybe.
Try. See, I think that should do the job. Guys, for anyone feeling that he's left behind or she's left behind, please, if you have a question why the other guys are working, please ask me so we can discuss it if you'd like. Everyone can put their computer on mute if we are disturbing anyone. Please let me know if you have anything that you would like to discuss. Anyone calculated reactions?
Just a minute, almost finished.
Okay, thank you. What kind of language you guys writing there, Emma and Bruno? Or is that done?
Yeah, is
They're saying it's done, right?
yeah, but it's not meaning. Sorry.
Okay, no, it's all good, all good. Okay, Mr. Leo, you were laughing endlessly when we're talking about Brunei. Can you please give us the answers then? Savio, please delete your answers. Mr. Savio, I told you do not write your answers.
Oh, sorry.
That's all good.
They might be wrong.
Well, let's see. Wait and see. Mr. Leo, are we done? Hi. How you doing? Not yet? Okay. I'll wait for you. That's all good. I'm waiting for you. When you're done, please put the answer. Let me know. So we've got slightly different answers from different people, from Benson and Saverio. So could you please not type your answers on the chat, please, until we say so. I want everyone to be involved as much as we can. Thanks, Fabio. Okay, thanks to you guys. There's no need to wait for Leo. We got lots of answers out there already. Anyone will disagree with Bruno and Benson? Or anyone will agree with Saverio? Can you please type your answers, in other words, please? $17 and 34 point something. Okay. So double check that. Got the correct answer for the first one, Saverio, 34.25. Looks like when you've done the adding of these forces, you made a mistake. So these numbers, they look right to me, 17.75, 34.25. Okay, good. All right, guys. So if that's our shear force, if that's our free body diagram, and we all start working on the shear force diagram based on what we learned. Simply, this is your free body diagram. we have a reaction in there, and these reactions are where are we? At A 17.75.
I still can't find why, because I'm getting 19.25.
Well, how did you calculate that 19.25?
Did you confirm that it's 17.75?
Yes,
Okay, sorry.
that's all good. Just simply, did you must have, because you got the similar answer here, you must have taken moment around A first, and you got that value first, right? Severio?
Yes.
Okay, so now we've got 34.25 acting upward, minus 12, minus 40. What would that give you?
So we're not considering the momentum of 3.
You can't consider moment 3 in axial forces or shear forces. That's a moment. These are forces, are completely different things.
Because I found the 4. Yeah, I did a mistake because I converted into the force.
No, you don't know. This will be taken only when you take moments. Okay. This would be considered when we take moments. If we don't take moments, we don't consider this at all, as we agreed.
Okay, yes, sorry.
Okay, all right, guys. So let's move on to shear force diagram. Anyone will start with that? Anyone will tell me, first of all, if I draw the beam here. This is the beam roughly from here all the way to about here. Okay. And exit that. So what should I do first? We're starting from left to right. Anyone?
Aaron?
Yes.
I just sent to you.
Okay.
Like, or should I erase it or what?
Yes, please. we will send them afterward if you'd like, but for now, if you could just delete the message until we make sure everyone following with us. All right, guys. So just tell me the step number 1. What should I do here? At point, we agreed this one, A, B, I think we said this is C. Is that what you said? C and D? Or the other way around? Ina, do you remember? Which one is C and which one is D we agreed on?
The opposite?
The opposite, okay. That's D and that's C. So if I'm starting at point C here, what shall I do?
No forces.
So?
Going to the right.
Okay. So that's good, Hannah. So simply what we do, we are starting at 0. Is there any shear forces here to make any change? No, but there's a moment. What shall I do about this moment? Guys. Fabio, what shall we do about this moment?
Sorry, Aaron. I was still working out my exercise.
That's okay.
The
Okay,
force here.
Yeah, sorry. You have a question? Go ahead, please. Saying something? And Paolo, what shall I do there at point C? What shall I do about this moment here?
Sorry?
Nothing.
Yep. So we have to do nothing about this.
Yeah, nothing.
Okay, so guys, I just want to make sure that it's clear to everyone. When we have a moment, it doesn't make any difference whatsoever on our shear force diagram. This is only shear force diagram. It has nothing to do with moments. So I'll be at 0, even if there's a moment, stay at 0 until I hit the first point where I have a shear force, which is the reaction here. From here, what shall we do?
Going up 17.75.
Perfect. Let's assume this is each square is 20, that's 17.75, just a little bit less than 20. And then from there, what will happen afterward, Bruno, from this point?
Into minus 27.25, I think.
So we're starting at 17.75. And then in theory, what will happen and why did you come up with that number?
Go horizontal on the left, and then you go down minus 22.25.
So you're saying go horizontal?
No, with a slope. Cross
Decline.
in a diagonal, yeah.
What about
To be minus 20. Minus 22.25.
Stella, can you please just say again what you had in mind?
What I was thinking, I can change this UDL by a punctual force located in 2 meters after the A, which has 40 kilonewtons. And then you can analyze the UDL as a force. But so in 2 meters after the point 2, I'm gonna go down 40, so gonna give me minus 22.25, but this gonna give me an inclinated line.
I have to stop you here because I don't want anyone to remember this and start making this mistake.
Aaron,
this is a wrong. Please, we don't have to do that. Please, okay? Just 1 second. Sorry, guys. Stella, we all agreed. If I have a UDL, when I have a UDL, that means straight away I'm thinking the first thing. So you see, guys, this is the difference between the way I deal with it and maybe the way you guys dealing with it. To me, I know a point cloud, that means I've got line up. I don't care now about the values. All I care about the shape. How much? That's where I care about the value. I'm here. I'm looking, what is the force? UDL. I know for a fact, straight away, the shape will be line like that. I know for a fact. It's not going to be, I don't have to think through it. Is it like that? Is it, I know straight away it's a line, declined line, straight away. That's the decision already made because I've got UDL. I've got UDL, that means I've got decline. Now, how much is a decline? That's the second question I asked. It's 10 by 4, 40. That means I have to go down from 17.75 to, you see, now I don't care about the reaction here. Because if you followed what you had in mind before, that means you should go down to 34.25. I don't care about this value here. All I care about, I'm at 17.75. I have to go down by the amount of this force, which is 40 kilonewton. So I've got 17.75, take 40, and that will take me down to 22.25 negative. So I look at it here. At this point here, this is the end of the UDL. It's not because of the support, because that's the end of UDL. At the end of UDL, I have to go down to 22.25 negative. That's where I decide the line has to go between these 2 points. Someone was asking me, was it Tiago? Tiago? or Paolo? Sorry,
No, it was me. I was just going to
Fabio.
try, but because you can solve this graphically, because you know that every 1 meter you have to go down 10 meters, so you can split. You can divide. Yeah, divide the space 4 meters by in 4 parts, and going down every part 1 meter, 10 meters or 10 kilonewtons, and then you just and then you just draw a line.
Okay, perfect.
This is one way of doing that.
Yes, 100% correct. And that way, what you're saying, it's exactly the same as rather than doing it for 1 meter, we can do it for the 4 meters. For the 4 meters will be this multiplied by the distance, 40. I started at that, and then I go down by 40. That's what we did exactly. Because sometimes, Fabio, what will happen, this value could be 12.75, for example, kilonewton meter. And the distance is 6.87. Good luck working out the maths of that, right? So it's just easier. Take the whole portion, multiply it by each other, and reduce the value. Now, so we are agreed that we are at negative here, negative 22.25. We have that value there. Adding 34 upward, what we'll do, that's an easy one. We're going to go upward by 34.25. I'm already at 22 negative, adding 34. That will make it, I think 12 will be upward. Correct. What will happen after, guys?
Go straight.
Perfect. There's no change between these 2 points, and then going back to 0. All good. So that is positive, that is negative, that is positive. This area here, what I care about, what we'll be using for our next bending moment diagram is this area here. Because if you think about it logically speaking, guys, let it go up again. I'll just 1 second. Leonardo, sorry, mate, Leo. Went up, sorry, Leo, it went up because we had, look at it, we had a force, point load, acting upward. What did we agree on a point load acting upward? What would that do for the shear force diagram? We'll make it jump by that value. We were at negative 22.25. Yep, all good, mate. And that jumped by 34.25, went to 12. Guys, if you notice now, if you try to connect things together a little bit, if I integrate the area here, that gave me the change of shear force diagram. The integration of the area under the UDL gave me the change in shear force diagram. Word integration, that means if I calculate the area here, which is 10 by 4, 10 as a magnitude by 4. 10 by 4 made 40. My shear force diagram changed by 40, negative. Why? Because all of this is negative. This similar concept, we'll use it down the track. That's what I'm saying to you guys. Keep in mind which one is positive, which negative. We will use it for drawing the bending moment diagram down the track. I'll be integrating this area to draw the bending moment diagram. I need to know, is it positive or negative? Because that will tell me the direction. Negative will give me always direction down. Positive, we'll see it in a minute, will give me direction up. We'll talk about it. Okay, so we're clear on the shear force diagram here. We have one last case, uniformly varying loads. Any question about this example, guys? Okay. So just keep in mind that's the solution there. And please keep in mind that the applied moment on the beam, 3 kilonewton, please Just remember this, because sometimes it may confuse you. Remember, does not make any change to the shear force diagram. Look at it. Didn't even affect it, as if it's not there. Moment doesn't change shear force diagram. Point load will make it shift. Bless you. But moment like this will make a change later on when we start talking about the bending moment diagram. Okay, the last thing we've got, UVL, which is a bit more interesting. Now, since we got that understanding, any questions about those, guys, about what we went through so far? Okay, so what we agreed on so far, just to recap on this, make sure we're on the same page. If I have a point load, upward or downward, if it's downward, that will cause the shear force diagram to dip down. If I have a point load upward, that will cause the shear force diagram to jump up. We're drawing orders from left to right. Okay? If I have uniformly distributed loads acting downward like this, that will cause the shear force diagram to be declined line. If for any reason, I may have another example of, like for example, wind pressure may create what we call it uplift winds. The UDL acting upward. This is the roof, and the wind trying to suck the roof up, trying to make the roof fly off. If we have that case, that means this will create a shear force diagram going upward, because that's a positive. The direction there is positive, upward. This is the direction is negative. So far, if you think about it a little bit, the shape will tell me the shape. The direction will tell me the sign, sorry here, that's negative sign. That gave me direction downward. That's positive sign. That gave me direction upward. So far, we have two variables. And these are the three rules that we need to follow. These are already two of them. The integration of the shape by having one point load that will give me a vertical line, upward or downward. If I have a straight line for the UDL, it's a straight line. Like these UDL forces, we always make them like this, straight line. That should give me declined or inclined line or diagonal line or a line with a slope. We will learn now the third case. If I have already my force, rather than being uniformly distributed load, if I have the third case, which is if I have uniformly varying load. You remember these type of forces? Anyone would guess what would be the shape produced by this? Regardless direction, all of this, but what would be the shape?
What? Of what?
Of the shear force diagram. So all what I've been comparing here, if you noticed, guys, look at guys.
It will be, if you integrate this one, you have a second degree polynomial. So it'll be x squared.
Perfect. Will be a curve, parabola curve.
Hyperbolas.
Yeah. So all what we're showing here on this side here, I'm showing the force, the shape of the force. On this side here, we're showing the response of the shear force diagram, or the shape of the shear force diagram. If I have a point load acting downward, that made a dip. If I had a point load acting upward, that made a jump. If I had a straight line, UDL, negative, that made a declined line downward. Negative gave me downward. UDL fixed value gave me a declined line. Straight line, integrate this. The integration of a straight line will give you declined or inclined line. The integration of straight line, the same. Will give you declined or inclined, or we can call it sloped line or diagonal line. But which one is positive or negative, that will tell you if it's going down or up, declining or inclining. Now, if we already have our force as a declined line, so guys, the equation in theory for this line here,
sorry.
that's okay. The equation here for that line equals to wherever, say, for example, 10x plus 3, for example. It's the first degree line with a slope on it. If you integrate this, will be a second degree or quadratic equation. So it would be, for example, where that y2 would be, for example, here we've got 10.
Would be 5 squared plus 3x.
5x, yeah.
5x squared on 2 plus 3x, right? So regardless, the important point for us here, that we have to change from a first degree line to a second degree curve, which will be a parabola curve. Parabola curve is either this way, this is a parabola curve, that is a parabola curve. What else I can say? This is a parabola curve, and that is another parabola curve. The question is, which one of them? That's what we're learning. Because all of them are parabola curve, but this is, for example, increasing, this is decreasing, this is decreasing facing up, it could be decreasing facing down. This is increasing facing down, could be increasing facing up, right? We have 4 options there. Which one of them will be able easily to tell?
Yeah, you should analyze the rate of increasing.
Perfect. Okay, so we have to look at that. Paolo, mate, you're killing your maths. What's going on?
Yeah, you asked us to participate, so
well done. I'm telling you, I'm very happy to hear that. No, I'm just saying that's good. You're following up on your maths. So did you have any background with maths, or what was it?
Yeah, I have a bachelor in physics.
Ah, there we go. There we go. Perfect. All right. Hopefully then you make a great engineer down the track. And all of you guys, I had students in previous, just to let you know, I had students in previous classes. They had business degrees, interior design degrees, no background, just straight from year 12, Australian students, a whole range of students, okay? Our process here to make sure at the end of all of this process, what we're learning, we all would be at the level of knowing to operate any of these calculations or to finish any of these calculations with confidence, guys. I guarantee that for you. All I'm asking you at this stage, could you please put the effort from your side, from your end, and be open-minded towards it. Don't be threatened that if someone knows more than you. Just to let you know, by the way, when I started studying engineering, a long time ago now, I started as environmental, civil engineering, but I was thinking, or I like maybe to start specializing at environmental engineering. Why? For a pure reason, honestly, at that time, I was thinking it's a new area. At that time was just, people are being very passionate about environment. That could be a better way for the future, all of those reasons. And it took me about a year and a half, which is I've decided, nah, it's not for me, I can't do it. It's too much legislations, rules, and memorizing this and that. I know myself, I love physics and maths more than theoretical information. The point I'm trying to make here, that you may start something that you don't find yourself at, and then you have to change for something else. Obviously, there's some people already been doing that for longer than you, so you have to catch up with them. I've got lots of students, they surprise me now at their final level now at our degree, associate's degree. They changed 180 degrees since the start until now. They started with just not knowing, not remembering any of the trigonometry rules, all the way now they are one of the people, they're getting full marks on all their quizzes for structural analysis, which is the more complicated subject. So what I'm saying, guys, please, I want to see every one of you and each one of you just participate as much as you can. And well done, Paolo. Thanks for that, mate. So for the UVL values, what do we have? Slightly different rule. Okay, that's good, Hannah. So slightly different rules. We have one extra measure to check. First of all, we do what we learned about UDL. We say if it's negative, that means will be declined. Positive will be inclined. The thing here, the inclined or declined, it's not a line anymore, it's a parabola, because we already started from a declined or inclined line, you remember? That was a declined line. So the integration of that should be a second degree equation, which is a parabola shape. Therefore, the shape will be a parabola for the shear force diagram. Inclined or declined, that will be depending on is the shear force positive or negative. The third thing now, we need to know, and you will see it down the track, the third thing you need to ask yourself, where does it face? Does it face upward or downward? And that will depend on the rate of your shear force. In other words, if you don't want to go too much in details for it, ask yourself a very simple question. Is this force increasing or decreasing? If it was decreasing, it would be facing down. If it was increasing, it would be facing up. The parabola shape. So, if I will ask you this question here, for example, if I have a beam like that, and I have a UDL, this is the beam, and I have a UDL here, starting from 0 to 5, the maximum value 5 kilonewton per meter. The question is for you guys, and please, Paolo, hold on a second, and don't just give them some chance. The question is for you guys. First of all, we agree to start with, this is negative. Agree? Anyone agree on that? Anyone disagree this is negative? It's negative, right? Because we agreed any of the forces above downward, they'll be negative. That means I know for a fact the shape I will be drawing will be going down, declining, regardless wherever, line, parabola, wherever it is, going down. That's what the negative telling me. This is already a line on a slope. Line with a slope. That means the shape should be parabola here for sure. All I know now, it's a parabola going down. This could be the case, or this could be the case. These are the two cases we have at this point here. Obviously, we have reaction, all of that. I don't care. All I care about now is this portion here. These two cases, they meet the criteria. Both of them are going down. Look at them from higher value to lower value. Both of them are parabola shapes. The only one thing I don't know, does it face up or down? And to answer this question, we said, if this force is decreasing, should be facing down. This one here, facing down. If this force increasing, should be facing up. In this case, what do you reckon? Should I choose facing up or down? Please, before you answer straight away, think about it. And write your question, write your answer down, so in case, so we can discuss it. Write your answer down on your paper. You don't have to write it on the screen. In this case, is the curve facing up or facing down? If you guys all written your answers, please go ahead and let me know. So, what do you reckon? Who was going to, was it Stella or Ina?
Why two of us?
Now, because I heard one of the ladies was saying something I didn't catch. Who was it?
It was actually me.
Okay, fair enough. Sorry for that, Severia. Then
It's all right.
sorry, mate. I just heard a noise. Yes, go ahead. So, what do you reckon, Severia? Does it face up or down in this case?
Okay, I know the rule about the quadratic equation, which says that if the x coefficient is positive, it's a sag curve.
Fair enough.
So this case is the second one. It's a sag.
This one here.
I can't see. Yeah,
No.
yes, that's one.
Okay, so let's put here next to it S for Severia. What do you reckon, Mr. Paolo?
Should be the other one.
Fair enough. And that's Paolo here. All right, guys. Who else?
Yeah, I agree. The first one with Paulo.
Paolo, because he's your friend or what?
No. It's because
Brazilians against Italian.
we start very low force and we'll grow in the force. So we start very low and then we'll increase the force. So the first one.
So increase. Just keep in mind, guys, what we said. If the force is increasing, the parabola should be facing up. When I'm saying facing up, that means the curve is facing up. So the rule says if the force increase, F increasing, that means the parabola should be facing like this, up. And I assure you, that is the rule there. If force is decreasing, the parabola will be facing down. So in our case here, what do you reckon? The force is increasing or decreasing to start with?
Decreasing.
Decreasing. Why is that, Ina?
So I choose the same as Paulo.
Okay, perfect. So it is correct. This is the answer, guys. But I just want you to, first of all, I prefer that as many can make this mistake, so you don't make it in the future. The reason is it's increasing, guys. Hear me out. This force here, what was the value of the force at this point here? The shear force. That was 0. What is the value at this point here? It's -5. We said this force is negative. We're starting from 0 to -5, that's decreasing. If the force is decreasing, that means the curve should be facing down. Okay? If I had it the other way around, if I had the beam that way, and I had the force going this way, and that's 5 kilonewton per meter acting here. Now the force is increasing because when we are saying it's 5 as a magnitude, but look at it, it's negative. It's in the negative direction. That means we are starting at -5 and we are going to 0. That means my force, my actual value of the force as a vector increasing. That means my parabola shape here, first of all, this is a negative force. I know that for a fact. That means it's down. This is a declined line or a line with a slope. That means we could produce a parabola. But the value of the force is increasing from -5 to 0. That's going in the positive direction. That means in this case, my parabola is facing up. Okay. How did we go with that? Let's read let's read the rules to start with about this, and then we take some example. Hopefully that will clarify things for us. So again, the same as the UDL, if we have a UVL, uniformly varying load, acting downward, that means negative. Negative will tell us direction. So negative, that means I've got a direction going downward. Because this is a UVL, which is an inclined line or declined line, that gave me the shape, which is a parabola in the shear force diagram, integrating a line with a slide that will give us a parabola shape. And the last thing I need to know, to be able to know this parabola shape, does it face up or down? It's by knowing if the force before is it increasing or decreasing in magnitude. If it's increasing, that means it's facing up and there will be a sag curve. If it's facing down, that means it's, if the UVL is decreasing, that means the curve is facing down, and that is a hogging, what we call it, hogging curve. It's the opposite of sagging curve, hog curve. Please, if you are the first time hearing these two terms, get used to them. In engineering, civil engineering mainly, we use them a lot. When you learn about slabs, when you learn about road design, when you learn about beams, sag always refers to the smiley face, hugging sad face, the opposite direction. Okay? Let's look at this example. Let's say we have a force, wherever it is, this W0, doesn't matter, it's not important to us, the value. Can you guys start looking at the shear force diagram for me here? Based on what we learned. First, before we do this example, can you please guys let me know if you have questions? How are we going with the last one? The last one, guys, will be, it's just, that's the most complex thing we may come across. Because knowing this, that will make drawing bending moment diagram just like this. Very easy. And I'll recap on all of this at the end. Will make a bit more sense, comes together in a bigger picture at the end. Because at the end here, we'll put guys into a very small, very simple rules. How to come up with the shape, how to come up with the direction, how to come up with the sign. Okay? Can you please start thinking about the shear force diagram for this parabola shape? For this uniformly varying load shape. How about this? Let's take a 10 minutes break. We come back to this one. I want you guys just to refresh a bit, just have some water, coffee, wherever you want to do. Let's come back at 3 or 5, please, so we can make a fresh start on this and we can utilize the last hour with summarizing things. Thank you, guys. I'll see you soon. Okay, guys. Just waiting for everyone to join us back. So while we're waiting, Paolo, where did you study physics?
Back in Brazil.
Okay. Did you
Yeah, back.
work at all in your degree, or you just finished your degree?
No, I finished my degree, and I've been working as a teacher for 10 years there, just high school teacher.
That's
And
really
then I
good.
moved here. Yeah.
Interesting. Well, what do you think of my teaching skills then, mate? you have
Yeah, it's
more
really good.
experience. You have
Really
more
good.
experience in teaching than me.
But teaching, I know it's a thing that you need to have to born with that feeling that try to help people. And if you have these, you can be a good teacher.
You're right. I was always frustrated from when I was at uni, when someone, not just uni, in school, when someone just not teach you something or not make it clear, and you spend another year or two to research it for yourself and try to understand it and why and how does it happen, just makes lots of frustration about why couldn't you tell me that from the start? As simple as this. It's a very easy concept to understand. And that created some kind of frustration for me, that a passion that, you know what, always maybe there's an easier way to simplify things. So yeah, you're right about that. Okay, guys, back to engineering mechanics. No, thank you, guys. I'm not into teaching. I don't have time, honestly, Fabio. Like, I'm just, if you keep up with the subjects that we're going through, the main subjects I'll be teaching you guys, structure analysis, structure drafting, and civil drafting, and engineering mechanics, okay? And the final project, it depends on each semester. If we have time, we usually split the projects and the students between us. We'll see how that goes. But anyway, I think you'll have enough of me. I'll bore you to death within the next few semesters. All right, guys, let's go back to our shear force diagrams for now. In terms of the shape, can I ask you all straight away, looking at it, what would be the shape of the shear force diagram? Just looking at it. This is the sequence of thoughts coming to my mind when I'm looking at a problem. The first thing I think of, the shape. What is the shape for the shear force diagram? Anyone will be able to tell me from looking at this beam here? Thanks, Paolo.
Curve with the increasing value.
Yep, well done, Gian. So can you say it again, please?
Downward curve with increasing value.
Okay.
So that's in the previous slide.
Okay, perfect. So the first thing we established, guys, that's please focus with me, because this will make it easier for you. The first thing, the sequence in my mind, that's what I'm thinking. The first thing I need to establish is the shape. Always think, first of all, what shape of shear force diagram will come up. When I see declined or inclined line, doesn't matter, line on a slope, that should produce curve. Full stop. That's question one. What is the shape? It's a curve. Because that's a line, that means the curve is parabola, second degree curve, quadratic equation, if you'd like to know the details of that. So the first question, what is the shape? Is a curve for the shear force diagram. Why? Because I had a line with the slope. The second question, where's this curve? Going up or down? I don't care now, is it facing up or down? I'm not saying is it going up, facing up like this, or up facing down. I'm saying, is the curve, the overall curve, is it increasing or decreasing? And I'll tell that from the sign. What is the sign of this force?
It's increasing.
The sign, what is the sign?
Positive.
Negative.
Negative sign. That will give me decreasing. Negative will give me decreasing curve. So all I know now, it's a curve, decreasing. Perfect, almost more than half of the answer. So I've got two options now. Is it decreasing facing up like this? Let's just draw that, options. What I got so far, because of the shape, it's a curve. Because this is negative here, that's a negative force. That means the curve is decreasing. I have two options. Is the curve decreasing like this, facing up? Or is the curve decreasing like that, facing down? That's the only thing I need to know. And I'll tell from the force, is it increasing or decreasing the curve?
Decreasing. Oh, increasing, sorry.
The curve, sorry, the force is increasing because it started here at a higher negative value, which is negative W, and then went to 0. So from negative to 0, that's decreasing. That means the curve is facing down. This is the correct option. This is wrong. Okay? So if I look at the answer for that, hold on a second. What did we have here wrong? That's
Aaron.
Yes.
So at the beginning, we have a high height, right?
It's increasing, guys. Sorry.
Yeah, it's a high height, and at the end,
Yep.
a lower height. So it should be the
Yep.
bottom one.
Yeah. So guys, that's, see, I don't think I can undo this. I can delete it. I made a mistake with this one. Talking too much myself. We started with a negative value and we went to 0. Negative to 0. That's increasing. Let me just change that. So I started with a negative value and I went to 0. That means this is increasing. Okay, so let's say that W, let's say it's 5. So I started with negative 5 and I end up with 0. Which one is higher? 0 higher than negative 5. So my value of the force increasing, going that way. That means this is the correct one and this is the wrong one. And sorry for that. So that's it. That gave me the curve. Now, how much the value here? That's the question you may ask. I know the shape. I know exactly how does it look like, but I need to know how much do I need to go down. Again, from the rules of integration, it's the area underneath this triangle. If you calculate the area of this triangle altogether, the same what we've done for UDL, we calculated the area underneath the rectangle. Now the shape of the force is triangle. The area under the triangle equals the value here, from here to there. The area of this triangle, W times L divided by 2. Negative WL on 2. All good? So you guys see how easy it will be for drawing the moment diagram, the bending moment diagram, based if we learn these concepts, what we're learning, which is I'm going to review them all together at once now. But if we get to that point that we learn them properly, look at it. It's exactly the same process. First of all, I'll ask myself, what is the shape for the bending moment diagram? I have a second degree parabola or second degree curve that will produce, in our mathematical understanding, if I integrate that will produce a third degree curve. I don't really care how you want to draw it. I'm not asking you to draw it accurately or anything. All what I care about, the values you establish and the shape of that. So I know for a fact it's a third degree curve. But is it going up or down? Let's think about it. This is all in the negative, right? We agreed this shear force started from 0 going all to a negative value here. So that means it's going down. The third question we need to ask ourselves, is it facing up or facing down? Again, is it increasing or decreasing? Look at it. We are starting from a value of 0. We are going to a negative value. This time, is it increasing or decreasing? We're starting from 0. We ended up with a value of negative.
Decreasing.
Decreasing, that means the curve facing down. See, so if we nail the shear force diagram, bending moment diagram will be just very simple for you guys, which is exactly the same thing, just we're taking it one level up. And this case would be the hardest case of all of them, which is not hard really. It's just the most advanced one between them all. You'll see the other ones, it's way easier. Let's take another example now. Let me just fix that for you. Okay, this example now. Slightly different than the one before. Can you please all draw your shape for the shear force diagram on your paper based on the discussion that we talked about? Leonardo, you had a comment there. It's always the opposite. Do you have something? Which one are we discussing?
So I was talking about the last one because if the
Saying
force,
bending moment
yeah,
diagram is always the opposite of shear force diagram.
yeah, for example, if it's decreasing, the curve gonna be increasing. Am I right?
Let's. I don't think so. We'll take some examples. We will see them all, but that
Ah,
shouldn't be the rule. We have to go through the process, and I'll remind you of this as we go on the first example. Okay?
all right, sorry.
No worries. No, it's all good. Thanks for the question. Very valid question, and I'm sure lots of students are thinking that way. Thanks for bringing it up.
Thank you, sir.
Anyone get it done, guys? Who can explain it to us? How we're gonna deal with this one? Gian is done. Perfect. All right, Gian. Paolo, Gianna. What does it mean, Diana?
Sorry, I'm Gianna. Yeah.
Okay.
So,
All right.
Gianna. It's typo, I think.
Yep. Easy. All good. So, do you prefer if I call you Gianna?
Starting with J, Gianna.
Sorry, I couldn't hear you.
Starting with J, it's Gianna.
Gianna.
Yep.
Okay. Yep. Okay. Thanks, Gianna. All right, Gianna. So, do you want to tell us how we should do this?
Yeah, so step by step, like you, and then
If you
you
don't
have
mind.
to go through. Yeah,
Okay.
it should
So
be.
let me just take this to our whiteboard again.
Yep.
And we can deal with it. So,
the shape should be curved because it's UVL.
thank you. That's a very good starting point that she's following the process. So the first thing is asking about the shape. Shape is, can you say it
Should be
again?
curved.
Curve. Second
Yeah.
degree curve, right?
Yes,
Perfect. So the answer for that, curve.
has to be downward because the value is negative.
And you're saying it's going downward direction.
Yes, because the value is negative, value of force.
Perfect. Downward. Because because force is negative.
Yes.
Yep. And
then it has to face to downward as well because the value is decreasing.
so the curve is a sag, I'd say. Is it? Sorry, it's a hugging.
Yeah, I think so.
Yep. Let's go hugging curve.
Yeah.
And because of the force started here from 0 and went to a negative value, that means decreasing.
Decreasing.
Okay, force. Perfect. So that's what Gianna.
Yes.
No, sorry, I'm saying that's what Gianna agreed on doing. Okay. So let me just see if I can get rid of these two. Those should be going. Okay. Finally. So what Gianna said that we got, the first thing she looked at, the shape. I've got a declined or inclined line that should give me a curve. That's the first thing, shape. See, shape is curve. Second thing she looked at, the sign of these forces is negative. Force is negative. That means curve is decreasing or going downward. Third thing she was looking at the actual force. Doesn't matter negative or positive, it's decreasing because started from 0 and went to a negative value, negative W. That's decreasing. Force is decreasing. That means the curve facing down. If you'd like to memorize it that way, facing down. So we came up with a curve going down and facing down. Shear force diagram, easy done. And obviously you don't have to write this. This is your analytical thinking in your mind. All what I know, I'm starting from here, drawing a curve, going down and facing down. Something like that. How much the value here? Gianna, would you have an answer to that?
Yes, L multiply by WO.
L by W.
By 2.
Yep. So the value here, perfect, is the area of this triangle, always the area of the curve before equals to the maximum value for the curve after, because we are integrating. So if we integrate this shape, we have the value there of WL on 2. And obviously that's in the negative, so it's a negative value. Leonardo, Leo, if you don't mind, can we look at this? This is your shear force diagram. You see, when I'm drawing bending moment diagram, I don't really care about force anymore. That's it. This is my shear force diagram. That's all the information I need for bending moment diagram. So, Leo, if you're looking at this shear force diagram based on the same understanding of these questions, let's try to analyze it. Would you be able to turn on your microphone? That's to answer your question.
Yep.
So, what's the first question we should ask?
The shape.
Perfect. So here, what we got here, this is a second degree. So what would be the shape integrating this shape? Would be a third degree curve.
Oh, yeah.
Okay, so a second degree will be integrated to a third degree curve. We know the shape. And you may ask, how is it different? I don't really care. I don't want you to worry. As long as you know a second degree or third degree curve. What we need to know here is the second question. What would be after we know the shape?
If it's decreasing or increasing.
So how would we know that? So the shear force was increasing or decreasing if the force was positive or negative. Bending moment diagram will be increasing or decreasing, increasing this way or decreasing that way, if the shear force is positive or negative. What is the shear force here? Is it positive or negative?
Negative.
Perfect. That's why I told you when you guys draw the shear force diagram, show where the areas are negative and positive. So that's negative. That means the curve is going down, right? Or decreasing. Now the two options, that's your question. The two options are saying, is the value of my shear force diagram here, is it facing up or down? What do you reckon?
I would say down, but I think that's up.
Why is that?
Nah, because I got confused. Sorry.
So that's on the briefing. Let me just take you back to this one here. The previous example, you said that the moment should be always opposite of shear, right?
Yeah, that's right. Yeah.
Now we got the shear force already in this example. The shear force already facing down. So based on what you're saying, that should be facing up. But
yeah, you're right. Yeah.
without worrying about these short rules, let's do the same thing. Is our value of shear force increasing or decreasing? It started from 0 and went to a negative value. What does it mean? It's decreasing. That means even the bending moment diagram is decreasing or facing down. So the bending moment diagram here will be something. I'll redo it. Bending moment diagram here will be something like that. Anyway, just it's easier here. So it will be something kind of like that, okay? Again, facing down. All what we have to say, so you may say, how did you draw it, Aaron, different than this? This is a 3rd-degree curve. How did you draw a 3rd-degree different there? I did not. I don't care about it now. I'm not going to draw anything here to measurement. All what I need to know this is a 3rd degree. This is a 2nd degree. The reason is because, for example, now, and that's the question even to Paolo, if I need to find the value here, that value there, what would be the value there, guys? Anyone will be able to tell me? What is the maximum value for moments?
Minus
Should we
W.
integrate this one?
Okay, who's first?
Okay, you go.
Hasanain?
Give a shot, mate. Give a try. I'll be.
Like I was saying, minus WL square over 3.
Minus WL square over 3. How did you come up with that?
I think it's the formula we saw before.
What was the formula that you saw before?
In your slides, I think.
Did I? I don't think I had that formula there yet.
I think I read it there.
Okay. Okay. So what is it? Sorry, WL square divided by 3.
Yeah, that's what I remember.
Okay. So just so you guys know, first of all, Hasanain, did you have another answer? Hasanain, I can't hear you if you're saying something. No, the same. Okay. So guys, I'll be with you in a second, Fabio. Just for you to know, guys, all what you are saying here, it's just simply, again, the same principle. It's the area of this, under this curve. The area under a curve, like this 2nd degree, the area under, put it this way, the area under triangle, like this, what's the area here? Let's say this is the height, this is BA, for example. The area of this equals to half B by A, right? Now, if I have the same thing, very simple, but a 2nd degree curve rather than a triangle, all it will be the area here, third A times B. So if I calculate the area of that, A, we've got it here as L, that's the length of the beam, that's third times L. B is WL on 2, so that will make it, so I need to make a third of that. That will make it, the value here equals to, the value here equals to that multiplied by third multiplied by W, so that will be negative WL square on 6. Correct? All good, guys? Just remember this is an easy one, very similar to triangle. The area of triangle, half the base times the height. The area of this shape under a parabola curve, it's the third of the base times the height. Easy. And look at that, we jumped into bending moment diagrams without even talking about them yet, which is, I didn't plan that today we're going to go through them a lot. I want you to focus, because as you've seen, the minute you nail shear force diagrams, bending moment diagrams will be easy. So, Paolo, sorry, Fabio, you've got a comment there saying, asking about, well, I think it can be a bit tricky. Can you turn your microphone on, please, Fabio? And
yes, I'm sorry. What I think
that's okay.
Is at the beginning when we have to draw the shear force diagram,
that part,
and we have to
look at, is it increasing or decreasing? Yes.
Yes, for example, okay, I know that this force is decreasing because it's 0 from 4 minus something. But if we don't pay attention and look just graphically, just this image, we can assume that the force is increasing because it looks like it's increasing, you know, just for the drawing.
Correct.
So we have to pay attention.
Yes, correct. So what Paolo is saying, guys, that just keep an eye on it. This, I made the mistake with it. If you noticed here, it's very easy to make the mistake on it. That just always keep an eye. Don't look at the shape. Look at the values. That's why you're saying, Paolo.
Yes.
So don't look at the shape of the force here for increasing or decreasing. Look at the values. I always, if you notice, if I need to know is it increasing or decreasing, I look at the value at the start, at the value at the end. That will tell me is it decreasing or increasing. All good? With some practice, guys, with after maybe 10, 15 mistakes, you should be fine. You should be all right. I just want to highlight, yes, questions?
May I ask you something just to see if I'm thinking right?
All right, mate.
Just by seeing the picture, I can assume that the moment, the reaction moment, inside the wall will be clockwise. Is that right?
So I've got the force acting this way. Yes, correct.
Yeah. So when the moment is clockwise,
yep,
we should add the value in the graph. Right?
We should add. So you're saying it's a positive?
Yeah, because at the beginning, the bending moment diagram starts from 0, and then going down to a negative point, and then go up straight to 0 again, because we need to come up to 0.
Yep.
And so I'm assuming that every time that we have a bending a moment clockwise, so we have to add, and if it's anti-clockwise, we have to subtract. Is that right?
Yes, that's correct. If, remember, what you're doing here, you are always looking at the beam at any point here, Paolo, what we're looking at, the beam from, let me just take you back to these slides, the right hand half of the beam. Let's go back. That's why at the start I made sure that you guys differentiate between the two. Along the entire beam, we're always assessing this half. Okay? We are always assessing this half. So the moment here, as we're assessing, look at it, the moment positive was counterclockwise, correct? Just, am I correct or not? Because that's what we assumed, moment has to make, sorry, clockwise to make this sag curve. Look at it. Yes?
That's really tricky. That's tricky. Yeah.
Yeah. Hear me out. All what we're doing along the entire beam, we are looking at this cross sections here quickly, every time. Okay. If the moment was in our beam here, if you look at this one, look at it. The moment always here. This force is creating moment this way, the opposite direction. That's why we are going negative. All these forces will create moment this way. Don't worry about the reaction now. Ignore the reaction. On this side, all these moments are, all these forces applying moment this way here. Rotating counterclockwise. If I take a cut here, the forces here are trying to create a moment negative way. That's why we're traveling in the negative direction. When we get to the reaction, that's where the opposite moment comes in place, which is will cause, that's a reaction moment you've got there.
Right. All right. Got it.
So look, you don't have to worry too much about it, as long as these are the rules here. If we are trying to do the numerical example like this one, we have to adhere. You have to think really through it, or not think through it. All you have to do, make your assumptions first in a positive direction, and then do these numerical examples. But if we follow the graphical way, you don't have to get to that point. Look how easy it is now. Just when you look at the beam, straight away, point load, that means I'm going down by 20, nothing going straight. I've got reaction here. If I calculate the reaction here will be, as we agreed, 46, going up by 46. That means I'm traveling 26, then going down by 40, then going straight, then going up by 14, which is the reaction here would be. These are the reactions. Look at them, 14 and 46. And bending moment diagram is as easy. Look at it, guys, from the same understanding. This time here, the shear force diagram is a straight line. What shape would that give me? Line on the slide, or diagonal line. Is it positive or negative, the shear force here? It's negative. That means my line is going down. I don't have a curve, so I don't have to worry about does it face up or down. That's it. I know it's a line going down. How much? The area of this shear force diagram here. This triangle, 2.5 multiplied by 20. Look at that, 2.5 by 20, negative 50. Then I go here. The shear force diagram is going up. This is the value there. It's straight line. That should give me a inclined or declined line. Is it inclined or declined? It's positive. That means should give me inclined line. How much does it incline? The area of this triangle rectangle. 20, sorry, that is the value there, 26 multiplied by 3. 26 by 3, that will be 78. 78, take 50, that will be 28, positive. And the same. So it's just, I'll go through it now and will make more sense altogether. But the point I want to make sure, guys, did we understand these arguments about the shape, about, in theory? Obviously, practice will put it more easier for all of you, but the theory behind it, did we understand how to make these decisions? We are all good with that? Anyone has a question about this? Okay. Now, let's go back to simplify things without worrying too much. Now you understand all of the processes that we went through. And now I'm telling you my personal method. If I want to draw any shear force diagram, a shear force diagram or bending moment diagram. Let's focus on the shear force diagram for now. Bending moment will be the same. The first question I ask myself is the shape. I have to make sure I have to guess the shape correctly. Always, please follow the sequence: shape, sign, and then direction of the curve, if we have a curve. Not all the time you have to use this. But the shape, if I have a point load, we agree. The shape is easy, up or down, vertical line. If I have a UDL, the shape will be line on a slope, either declined or inclined. If I have a UVL, uniformly varying load, that means the next shape should be curved, second degree curve. If for any reason I had a second degree curve, that will give me a third degree curve. So the first thing, please ask yourself, what is the shape? Second thing, you know the shape, but you need to know, is the shape going straight? Is it going up? Is it going down? Obviously, it's either up or down. Especially if it's straight line, obviously it's going straight. But if it's increasing or decreasing line, what will tell us is it going up or down is the sign. So the sign is the second thing you need to ask yourself. What is the sign of the shear force? Is it positive or negative? If the sign is negative, that means the line or the curve will be declined. Line for UDL and curve for UVL. If the force is positive, that means when we're saying positive, that means this is going up, acting upward, like wind pressure. Negative, I don't want to call it negative, suction wind pressure. If we have that case, that means the force is positive. That means the curve or the line I'm producing should be inclining rather than declining. The third thing you ask yourself, well, if it was a curve, I need to know, is this curve facing up or down? And that based on the shear force before it, is it increasing or decreasing? I look at the first value, the last value, that will tell me is it increasing or decreasing, and that will tell me the shape going up or down. All good? So in terms of shapes, please, that's the first one here. It's either straight line, inclined line, declined line, sorry, either straight line or diagonal line, doesn't matter, inclined or declined, I don't care now, or curve. That's the three answers for that. Let's write them down. Options are straight line, line with a slope, or curve. These are the three options you've got from that shape rule. Don't care. Is it going up or down? I don't care. All what we know is with the slope. And the curve, the same thing. We don't care now. All what we know, what type of curve. Is it first degree, second degree curve? That's the answer you get from here. Okay, sorry, second degree or third degree curve. The answer you get from here, that's what will tell you the direction. Is it inclined or declined? The answer you get from here, that will tell you the curve facing up or the curve is facing down. Is it a sagging curve or hogging curve? That's it, guys. If you follow these 1, 2, 3 questions, no matter what the shear force diagram or bending moment diagram you're against, that will solve it all for you. And think how much work you're saving yourself doing all these steps. Especially, this is a very easy shear force diagram, bending moment diagram. Imagine you have a UVL here. That means you have to take a section at the start of it, then you have to do similar triangles, finding the value there, then a section through it. You've got lots of steps to be done. All right? So it's essential that we understand this method of shear force diagram, bending moment diagram based on the curve. There's one thing I would like you to keep in mind. Actually, where is that beam there? Let's take this as an example to understand. And we'll make it easier to all of you. With our reaction forces. All right, guys, can we all please try to draw the shear force diagram for this one, start with, for this beam. I gave you the reaction forces. That will take one step out of your way. Quickly, what would be the shear force diagram for that? Actually, I don't think we'll have time. Anyway, you've got that on yours. I don't think we'll have time to go through the point I want to make. We'll go through it next lecture. To start with, just so we can go make sure we are on the same page. Your homework would be on your tutorial booklet that you already have. You've got section 14. Yep. Section 14. You've got good variety, not really great. They don't have too many UVL. I'll send you some other examples down the track. But just those shouldn't take you time at all. See, all of this are part of the basic shear force diagram of what we need to do. Can you please draw the shear force diagram for these beams? As many as you can. At least I'll need, so you've got there, let's think about it. You've got about 23 examples, and at least I need 10 examples of each one of you. And actually, let's look at it that way. Let's do the last 10 examples in here, please. So your homework, please, everyone, until next week, 10 examples, the last 10 examples of those. And I will encourage all of you, that is a homework, the last 10 examples. And please email me that before the lecture by Tuesday. You've got, I will encourage all of you guys to even do those starting ones, which is, they are very, very easy. Each one of those, I'm hoping that by the time you get to the end of it, wouldn't take more than 5-10 minutes, okay? Did we record the last part here? Yes, we are recording, that's good. All right, guys, any questions about today's lecture? As always, when we learn something new, nothing new will just simply sink in without any work. Please, you need to practice it. Very important, as I said, for too many reasons. In the exam, you will have a big portion of the exam about this. In real life, you'll use it a lot. I told you it could be as simple as in your job interview, they may give you a very simple beam. You should be on the spot, capable of drawing shear force diagram and bending moment diagram for it. So in your homework, you're not required to draw the bending moment diagram. All what you need to do is shear force diagram, okay?
Okay.
All right.
So question number 1 from 1 to 20.
So you've got 1 all the way to 23 are there for you guys under section 14. I'm asking you from number 13 to 23 as a homework. Okay? 13 to 23 as a homework. Everyone must do those. From number 1 to 12, I would encourage all of you. Each one of those wouldn't take you long at all to draw the shear force diagram. All what we're asking for, the shear force diagram. All good?
Actually, I couldn't understand. So
Okay.
the homework is all of the questions?
No, the homework is number 13 to 23.
Okay. And then with the shear force?
That's the homework. Draw the shear force diagram from number 13 to 23. That's your homework. What I'm asking is, could you please spend the time, if you have the time and the effort to do, it's highly recommended that all of you do all the other questions from number 1 to number 12. So Bruno is asking just to confirm we will not have face-to-face classes, and when final exam will be. Can you turn on the microphone so I can't see the, and when the final exam will be? So we will not have, all right, so you know guys, what is the, why I'm saying I don't have the answers. Bruno, simply the instructions from the government to reopen in a staged manner, what they call it, okay? The higher priority first, and then the lower priority as comes after. Higher priority, for example, people they're learning carpentry, welding, electrical, they can't do it at home, right? Like they can't learn like us what we're doing on a screen. They have to do the practical work. These are the people are coming back to TAFE, I think, within a week or two. Us, they're scheduling us as a second and third priority. There is a chance the whole semester may go through and we won't come back for face-to-face delivery. In terms of the final exam, it is confirmed that that's the week of the exams. It's after I showed you the Excel sheet. It's the first week in July. That's the week of the exam.
Okay.
Okay. Now, when or which day is it on that? Even me, I wouldn't be able to know until these 2 weeks. In which day on that week? Why? Because we have at least 10 other subjects, and we have to come up with a way. Usually, the coordinator for all the rooms and this and that, they will coordinate how many people, what time, at what room. So it's something I don't even work on it. Okay. We usually get told we usually submit a preference time, and most lecturers what they do they submit their time of the lecture the same time as their exam. So we try to do it on Tuesday most likely about 10:30, 11 o'clock. Usually we do our exams, and that's for 3 hours, but I can't confirm now until we get to that point. Any other questions, guys? And mainly any questions related to the lecture?
Can you change my attendance, please? It's still on no.
And that's okay. You're going to promise us to be on time next time, Mr. Hassanein? What do you reckon?
Yeah, I'll be on time next time, I promise.
Okay, so you are under late for now. We'll see how that goes for next time.
Okay, thank you.
All right. So, guys, just all of you, please. Hassanein, if you can. Yep, thanks. Guys, all of you, there's endless examples online for shear force diagram, bending moment diagrams. Just try to look them up and see in case you had any issues, in case some of you guys will have a question during this week, feel free to send me on Teams and we will come back to or we'll find a way that we can catch up, me and you, okay? Yep, I've got some time, Paolo. I've got a meeting starting at 4:30, so, and I've got a phone call before that I have to do, so I have to be quick, but I have 5-10 minutes after that. All right, guys.
Sorry, Aaron.
Yes, mate.
Just about the quiz that we are going to have next week.
Yes.
So if we can do a quick recap about that.
Just recap, you mean?
Like it's going to be on the...
Method of sections for trusses.
Only method of sections for trusses.
Only method of section for trusses. Simply the tasks that you should be... the task that you guys should be capable of doing, obviously calculating reactions, taking a section, and finding these values of the members, okay?
All right, thank you.
No worries. All right, guys, thank you. Paolo, what I'll do, I'll just contact you on a different chat, okay? All right, see you guys, have a good one.
Thank you, Aaron.
Thank you, guys.
See ya. Thank you.
Thank you.